Recall that for the Laplace transform of function f of t, this is basically the improper integral 0 to infinity e to power negative st f of t dt. For power function t to power n, the Laplace of t to the n can be written as basically n divided by s times the Laplace of t to power n minus 1. We're going to use this and drive some formula. For example, suppose I ask you to calculate the Laplace of t to the first power. N is equal to 1, so I get 1 divided by s times the Laplace of t to power 0, or 1 over s, times the Laplace of 1. The Laplace of 1 is easy, can be calculated. The Laplace of 1 is equal to the improper integral 0 to infinity e to power negative st times 1 dt. Using a simple u sub, u is equal to negative st, du is negative s, dt, so the Laplace of 1 can be written as the integral of e to u du multiplied by negative 1 over s, so the Laplace of 1 is equal to negative 1 over s e to power negative st, t ranges between 0 to infinity. The Laplace of 1 is equal to negative 1 over s. If you plug in infinity, you get 1 over infinity, which is 0 minus 1. So the Laplace of 1 can be easily calculated as 1 over s. So the Laplace of t to the first power is 1 over s times the Laplace of 1, which is 1 over s, and you get 1 over s squared. Now let us calculate the Laplace of t squared. For the Laplace of t to power 2, following the formula, n is equal to 2, you divide it by s, and then multiply that by the Laplace of t to the first. But you already calculated the Laplace of t to the first, which is 1 over s squared. So this can be written as 2 over s times 1 over s squared, or the Laplace of t squared is equal to 2 divided by s to the third. Let's calculate another Laplace so you can see the pattern here. The Laplace of t to the third is equal to 3 divided by s times the Laplace of t squared. But the Laplace of t squared calculated beforehand, and it is 2 divided by s to power 3. So this is 3 divided by s times 2 divided by s to the third. So the Laplace of t cubed is equal to 3 times 2, 6 divided by s to the fourth. Perfect. What is the pattern that we see here? The Laplace of 1, t to 1 is 1 over s squared. So let us copy this guy down here. Just show you the pattern. The Laplace of t to the first is equal to 1 over s squared. The Laplace of t squared is equal to 2 divided by s cubed. The Laplace of t cubed is 6 divided by s to the fourth. Well, you can rewrite this as 1 over s squared 2 times 1 divided by s cubed. This can be written as 3 times 2 times 1 divided by s to the fourth, and you can continue this process. So basically, the Laplace of t to the n can be written as n factorial. When it's 1, you have 1 factorial. When it's 2, you have 2 factorial. When it's 3, you have 3 factorial. So n factorial divided by s to power n plus 1. So for power function, you can easily use this formula and calculate the Laplace. Let's take a look at a few examples for you. Suppose I ask you to calculate the Laplace of 2t to power 4. We're going to use the formula that we just introduced, but because of linearity, this can be written as, you can take this 2 and write it in front of the Laplace because of linearity. Or a scalar multiplication and eventually the same thing. You have 2 times the Laplace of t to the 4th. But for t to the 4th, you're going to use the formula that you just introduced. So you're going to get 2 multiplied by 4 factorial divided by s to power 5, which can be written as 4 times 3 times 2 times 2, which is 48, divided by s to the 5th. Another example for you. Suppose we want to calculate the Laplace of t to power 5. Well, following the formula that we just introduced, this is equal to 5 factorial divided by s to power 6. You can leave it like this, or you can simplify this as 120 divided by s to power 6. And as I mentioned before, for linearity, we can apply this formula and do the calculation. Calculate the Laplace of 40 minus 10. Again, here by linearity and then applying a scalar multiplication, this can be written as the Laplace of 40 minus the Laplace of 10, which is 4 times Laplace of t minus Laplace of 10, or 10 times Laplace of 1. This can be written as 4 times 1 divided by s squared minus 10 times 1 over s. So the Laplace of 40 minus 10 is 4 over s squared minus 10 divided by s. Let's circle each one of these so you know what we did. You can continue this process. For example, let me show you another example here. Suppose I ask you to calculate the Laplace of negative 4t squared plus 16t plus 9. By linearity, we can separate this into negative 4, the Laplace of t squared, plus 16, the Laplace of t, plus the Laplace of 9, or 9 times Laplace of 1. So you get negative 4, 2 divided by s cubed, plus 16, times 1 divided by s squared, plus 9 times 1 over s. Or you get negative 4 times 2, negative 8, divided by s cubed, plus 16, divided by s squared, plus 9 over s. So this is again by linear combination. We know that the Laplace preserves the linear combination. We can continue this process, calculate more quantities that has linear combination between them.